since we're talking about energy, so the process of going from a liquid to a gas, so we know that that's going to be called evaporation, or it's going to be called heating, or it's going to be called boiling. Okay. So, but just that concept of that phase change, right? We know that that phase change is going to take energy. It takes energy to sit there and free those molecules so that they'll be able to go into the vapor state. Now, if we take a look at our image here, this is representing that vapor state. This is a closed system. And so this is happening in a closed system. Um, and what's really happening is that we have molecules that are in a liquid. Well, they're getting enough energy so that they're able to escape that liquid phase. So it's going to take energy to sit there and allow that to happen. So then you have molecules that are going to be going into the vapor phase, but at the same time, you're also going to get molecules that are going to be coming back from the vapor phase back into the liquid phase. Okay. And again, for them to go into the vapor phase, that's going to take energy. And then this is going to happen, and if you're heating it up, it's going to happen until you reach a point of equilibrium. Let's say your temperature is finally balanced, or let's say it's in a hot room. You're going to get some of those molecules going into the vapor phase, and that are able to be free. But there's also going to be molecules coming back into the liquid phase. And again, if we leave it alone and let it happen, and we maintain that temperature, it's going to reach a point of equilibrium, because then you're always going to have some of those molecules that are going to go into the vapor phase and some of those molecules that are going to be coming back to the liquid phase. Now, during equilibrium, that rate, how frequently that's happening, is going to be equal. Okay. So you're going to get a point where you're equaling the amount that's just going in and out of the liquid phase. Okay. And that is going to be happening at equilibrium. And so for us to move more things into the vapor phase, that intermediate phase, to really break them free, we need enough energy that's going to be above a certain point. And that certain point is going to be called the heat of vaporization, or we'll call it the enthalpy of vaporization. Let me type that word in. Okay. So we'll use the term heat, or we'll use enthalpy. They're often interchangeable. Now, what that is, it's going to be the amount of energy that is going to be required to change 1 mole of liquid into vapor at a constant temperature and pressure. So we have to be maintaining our temperature, and the pressure has to be maintained. And so that allows us to go from one phase to the other phase. And it's like so like if we had a mountain or little hill, and let's say our car breaks down here on the side, okay, and we push this car up, right, to the top of the hill so that we can coast it down, right, because we know there's this gas station up the road, right? All we have to do is get to that coasting part, so that energy that it takes to get over the hump, okay, that's sort of what we're seeing here. So if you get to the point of vaporization, so let's say if we're talking about water, do you guys remember what temperature water boils at?
100 degrees.
Yes, that's right. It boils at 100 degrees. So as soon as you reach 100 degrees, not everything will go into vapor, right? It takes a little bit more energy. You have to get over that heat of vaporization to make things to go from liquid to gas. Okay. And so it's like a hump that we have to get over. So that would be the same thing. We'd have to push the car over this hump before we can cruise. Right? That's exactly what's going to be happening. You need a little bit more energy to get it to that hump and push it over so it can start sliding down. Right? Okay. Now the boiling point is going to be the temperature which the vapor pressure becomes equal to the pressure above the liquid. Okay. So things start to boil when those two pressures are equal to each other. And so it's going to be that temperature when those two pressures are equal to each other that's going to allow boiling to occur. Now, what's happening with those molecules, those water molecules, there's interaction between those molecules. Because there's interaction between those molecules, we call these interactions, we will call them intermolecular, because inter, like, have you guys, the interstate, you're familiar with the interstate?
Yes.
Like I-5?
Yes.
Yeah, okay. So you know that I-5 goes all the way from, let's see, the southern part of California, all the way up to uh, Oregon and Washington, actually, right above Washington. So it's between states. That's the reason why it's called interstate. Now, when we talk about intermolecular, that means between molecules, right? So we have two molecules interacting with each other. In this case, when we're talking about water boiling and water, we're talking about water molecules interacting. And so there's forces that keep those water molecules together, right? That makes it maintain its liquid state until it reaches a certain amount of temperature. Once it's above that certain temperature, 100 degrees, then you're able to get those molecules to escape. There's enough energy because you've gotten above the heat of vaporization to allow those molecules to escape. Okay. So it all is mush to me until I see a picture. I don't know about you guys, I need the visual. So this is our water boiling. This here is that liquid phase. This here is the gas phase. Now what's happening is that we need enough energy to go from the liquid phase into the gas phase. Okay. So, and that energy that we have to overcome is called the heat of vaporization. Now, this would be what we termed as endothermic. Endothermic means that we're putting energy into the system, right, to get it to that point. So we have to put heat into that system. We have to put enough temperature to allow those water molecules to escape. Okay. So then that would be endothermic. Endo meaning in. And then if we're going to be cooling it down, we need to release some of that energy, and that's going to be exothermic, right? And so the process of going from the heat of condensation, or we'll say the enthalpy of condensation, is going to be an exothermic reaction because we're going to be losing that heat. It's going to be escaping, okay? And so that allows that vapor to go back to a liquid. Okay, so you guys see those bubbles, right? So those bubbles there, they're going to be the bubbles of vapor that are going to be forming in the liquid. So then, in other words, these molecules are there moving so fast that they're kind of escaping within the liquid. And so these bubbles, you start seeing them coming up to the top trying to escape because they've moved enough to allow them to be free. Right? And so you're freeing those molecules by heating them up. Now, this process, we are able to calculate the amount of energy that's coming from this process. We will often say the amount of heat that is coming from this process. So when we make reference to heat or energy, they're kind of simultaneous because a lot of times the way that we associate heat is that form of energy. And the way that we're going to be doing that, Q is going to represent our heat, okay, or the amount of energy that's going to be required. M here is going to represent mass. And so this is going to be the mass, or it can also be the number of moles. Okay. So it could be quantity or it could be mass. It just depends on what our heat of vaporization is, what units it's in. Okay. So Q, so these guys, Q is going to be directly proportional to M. So in other words, as the heat goes up, the heat will go up with the mass, right? And for energy, right? So, or the energy is going to go up with mass. As mass increases, energy is going to go up. So in this case, we're using a proportionality like constant, and these are considered constant unless we go to a different phase, right? So that delta H is going to kind of represent that constant. And it's going to go up, not the delta H, but the heat will go up as the mass goes up, okay? And so that heat of vaporization can also be changed to Q over M, and that's going to give us how much heat there is for that particular vapor. Okay, and then the heat of condensation is going to be the opposite. So if we go back, see back to heat of vaporization and the heat of condensation are going to be, in terms of the absolute value, are going to be equal to each other. The only thing is the heat of vaporization is gaining heat, so that's going to be a positive value. It's endothermic. The heat of condensation is going to be a negative value, okay, because it's exothermic. But they're going to be the exact same value. Okay, so, and that's really what this slide is kind of letting us know, that we have exactly the same value for the heat of vaporization and the heat of condensation. Only thing, the sign is going to be different. Okay. So here, these are our various substances. These are their melting point. So this is when they go from solid to liquid. And then their boiling point, where you go from a gas, from a liquid to a solid. Sorry, from a liquid to a gas. And then the heat of fusion is the energy that it takes to cause melting to occur. So when you're going from that solid to a liquid phase, the energy that it takes to get over so that that will happen is going to be your heat of fusion. And then the heat of vaporization is going to be the heat that it takes a liquid to go into the gas phase. Okay. And you'll notice that they're all different depending on the element or the compound that we're looking at. Okay. So again, they're going to be different depending on the element or compound that we're looking at. Okay. So what we're going to commonly use for this chapter, we're going to be talking mostly about water. We may talk a little bit about iron. But water, we know that it melts at 0 degrees Celsius. So it freezes at 0 degrees Celsius, but it also starts to melt at 0 degrees Celsius. So in one case, when we're going from a liquid to a solid, we know it freezes at 0 degrees Celsius. If we're going from a solid to a liquid, we also know that it melts at 0 degrees Celsius. And it boils, its boiling point is 100 degrees Celsius. Its fusion is 333. Heat of fusion is 333. And this is joules per grams. So in other words, the units that we're using here are going to have to be mass, okay? Because we're talking about grams. You can also have it shown as moles. So in that case, it will be joules per mole. Either one of those, if you see grams, you know that you need to make sure that you're using mass. If you see moles, you need to make sure that you're using moles. Okay, does that make sense?
Yes.
Okay. And then the heat of vaporization for water is going to be 2.26 kilojoules per mole. Per gram, sorry, per gram. So in the case of the heat of fusion, we know, again, that's going to be mass, but it's joules, right? And this one is kilojoules, which means that it's 1,000 times larger than a joule. Okay, how much energy is needed to vaporize 118 grams of liquid if its heat of vaporization is 1.13 kilojoules per gram? So in this case, they're giving us everything that we're going to need for this problem, right? If we take a look at our equation, what was our equation earlier? wasn't it Q equals M delta H? Wait, okay. So we have everything that we need in this case. So what are we going to do?
You substitute the M for 188 grams, is it?
Okay.
And then the heat of vaporization with the multiply that by the 1.13 kilojoules over 1 gram.
Okay, so then our grams are going to cancel out. And then we multiply that. Pull up my calculator. What do you guys get?
212.
Okay. So we're going to get 212. And we know that we're only going to have three significant figures because both of these only have three sig figs. And you guys are professionals now. And you recognize that. Okay.
So I have a question. So you said enthalpy was just another word for the heat of vaporization?
That is correct. And so we would call it the enthalpy of vaporization.
Okay, thank you.
Okay. Now we know that energy is going to be required for those state changes. And so we also have other state changes because we were talking just about going from a liquid to a gas. So if we're going from a solid to a solid to a liquid, then we're going to be using the heat of fusion instead of the heat of vaporization. Okay. And so when we do that, it's going to be the same equation. The only thing that's going to change is the value for our delta H. So how much energy is required to melt 25 grams of ice at 0 degrees Celsius? So we're going again from a solid to a liquid. So in this case, we're going to have a value for our delta H fusion from that table that we saw earlier. It's going to be 2.26. Ooh, let's see, kilojoules per gram. Oh, let me make sure because I think I got it mixed up. I think it's the 33. Let's confirm. That seems way too much. Sorry, 33, 333 joules. As I said, it's been a long day. I had my first meeting this morning at 8, and then I've been going to meetings all day. So, and then getting a pie in the face. So, 333 joules per gram. Okay. Let's move that out of the way so we can actually see the full thing. Okay, so now that we know that question, so now that we know that, how much energy is going to be required to melt 25 grams of ice at 0 degrees? So what are we going to do? Which equation are we going to use?
Would it be the same one as the last time? It's the Q equals M times
That's right.
heat diffusion.
Okay, so then that's going to just plug everything in. So we have 333. Oops, let's put the mass in first. 25.0 grams times 333 joules per gram. You know, those grams are going to cancel out and we're going to be left with just joules. How many sig figs should we have? Sig fig for significant figures.
3.
We should have 3 sig figs. That's right. What do you guys get?
8.33 times 10 2.
Okay, so the actual value that you guys have, 325. So even though my lecture notes say that it should be 8.33 times 10 to the third, or 10 to the, yeah, 10 to the third power, um, really because this is exactly 5, it falls on exactly 5. Then the actual value, there's nothing following it. So it's kind of like that. If you guys look at a teeter totter and you have these kids that are exactly the same, nobody's being pushed over. Nobody's higher than the other because they don't weigh more than the other. They weigh exactly the same weight. So that teeter totter stays straight. Okay. So they both kind of stay elevated. Nobody's up, nobody's down, straight because they're the exact same weight. So in actuality, to be correct, Q is going to be equal to 300, I'm sorry, 8,320 because you don't have anything following that 5 to round it to make it greater than 5. It's exactly at 5, if that makes sense. And so in your text, so technically this would be incorrect. But according to the rule of science, because it's not greater than 5, then we're going to drop it down to 8,320. Okay. Questions?
I have a question. I think it applies to this and the last thing you went over. So how would you deal with it if it had like the mole, like you said, instead of like the over the grams?
Yeah, that's okay. So let's say, for instance, if this was, so if we had this as delta HF, it's going to be equal to 5,999, or so 599, 5,994 joules per mole. So in this case, what we would do, we'd have to convert this number into moles, right? If they gave us mass. The way that you'll go about doing that is we're talking about water, right? Because we know ice is just water, right? The chemical formula for water is what? Does anybody know?
Well,
That's right, H2O. So we know the chemical formula is H2O. So how many hydrogens do we have?
2.
H2O. We have two, right? So we have two hydrogens. How many oxygens do we have?
1.
One.
We have one oxygen. Okay. So then what we would do, we would go to our periodic table. So I'm gonna 1 second to pull up a periodic table. Okay. So then what we're gonna do is, since we know that we have two hydrogens, and I'm gonna put this is what happens when you teach like 50 million classes. And everybody's at different stages. I'm gonna slide this over in that blue space here. Can you guys see it right now? If I pull it over here.
Yes.
Okay. So we're going to look at the what we call the atomic mass of hydrogen, which is 1. So it's 1.008. So then what we're going to do is we're going to go 2 times 1.008. And then, which we know is going to be 2.016. And then for oxygen, what is that mass number for oxygen, or the atomic mass for oxygen?
15.999.
Yep. So we'll go 1 times 15.999. And so that's going to be 15.999. Oops. 999. And we're going to add the two together. So 2.016 plus 15.999. So that's going to give us 18 point 0.15. Okay. And the units for that is going to be grams per mole. Okay. So now that we got that, I'm going to go back to our other page, our slides. Pull that back up so that we can actually see it. Okay, so this is what we call the atomic mass. So we're going to use that atomic mass to change our grams into moles. So in this case, we have 25 grams, and we want it to be moles, so we want to have moles on top. So we're going to put moles on top, and then we're going to put grams on the bottom. So we're going to use our molar mass of water, say H2O here, since we know that ice is water. And then we're going to have H2O here. Then H2O here. Okay, so we have 18.015 grams. So that's going to be on the bottom because we want to get rid of grams and we want moles. So then moles are going to be on top. And that's since it's grams per mole, so it's going to be understood to be grams per 1 mole. So we have 18.015 grams per 1 mole. So then the grams of water are going to cancel out. And we're going to get 25 divided by that 18.016. So sig figs. So we want to keep 3 sig figs. So that's 1.39 moles. So now it's going to go through the same process. Your Q is going to be equal to, and instead of M, we call, when we're talking about moles, we call that N. So it'll be N delta HF or H fuse because this unit is now in moles. Okay, so then we'll have 1.39 moles of water times 5,994 joules per mole. Then our moles are going to cancel out, and then we're going to be left with just joules. So which should give us approximately the same answer. A little bit off, but almost the same answer. That's because we round it differently, so then if it's 3 sig figs, it's going to be this. Okay. Any questions?
For that 5,000 number that you first put up there, you just made that up or
Now,
was it from somewhere?
it's actually that value. Only thing is normally written as 5.9, And so it should have given us roughly the same answer.
And then what about the 333? How did you get that?
That's given to us in that table. One that we earlier. Let me go back to it. So remember this table here? We went 333, and that's going to be your heat.
Yeah.
So on the exam, they typically will give you the value, or you're going to be provided a table like this. You'll have to find it.
Okay.
Okay. Good question, though. Good questions all around. So does that make sense? And so you just want to, it's important. This is the key. The secret to chemistry is paying attention to units. That's why we made such a big fuss at the beginning of the semester. Because if you pay attention to units, you can make sure that your units are matching up and canceling out when they're supposed to cancel out. If you don't pay attention to units, then you often will make silly mistakes. Did everybody get that? I'm sorry. That was really rude. I didn't even ask. Now I can't get it to come back. Well, it's being recorded, and I forgot to show you that. That's what I wanted to show you. That's what I just remembered. And also a reminder, you know that if you guys are in Fireball, Coalinga, or in Lemoore, you guys can pick up the packets, the lecture packets for each of the lectures. They're available. And I have right now only have 5 that are there. If more people are taking them, then I'll print more. but if we run out before you guys get it. So you have the chemical packet, you have each of the lecture packets up until I think 11. And so now we're getting ready to start 12. And so I'll be printing out in my other class. We're starting 12 and 6 and 12, chapter 6 and 12. So I'll be printing those out and giving delivery. Okay. Okay, you guys ready? You want some more? Are you hungry? Not literally hungry, but you know.
Yeah, I'm ready.
Okay, good. So the next thing that we're going to be talking about is specific heat. Now, when we talk about specific heat is going to be within the range of a phase, right? And so when we're talking about that heat that we're going to have between that range of the phase that we're in. So if we're going from a temperature like negative 25 to 0 degrees, that's all in the solid phase or ice, right? Excuse me. And so since that's all in the solid phase, it's going to have what we call the specific heat for ice. And so that's going to represent the C value. It's going to be a constant that we refer to as the specific heat. And there's tables for it. Okay, so, and I'll show you that here in a second. We've talked about delta T. That just means change in temperature. So we're going to be looking at the change in temperature, and we're going to be looking at the mass. Okay, so it's going to be mass times C times delta T. Now, have you guys ever heard of the MCAT?
No.
Okay, the MCAT is an exam that you take if you're planning to go to med school. And so I often will remember it because MC and that delta reminds me of an A, and we know the T for temperature. Right? MCAT, that's how I always remember that equation. So I never forget it because of that. So Q equals MCAT. And so in this case, again, I will be providing you guys the equations for this. So those will be provided to you on the exam. I need to make sure that I upload that little link that I have for it, but they will be provided for you, right? Because you guys are going to get a couple of equations through the process. And really, I'm not going to give you the name of the equation. All I'm going to do or provide you what the symbols mean. That's going to be you remembering those things, okay? You're just going to get the equation, okay? So Q is going to be MCAT. So again, we're talking about heat or energy, right? And here we're going to be calculating energy within phases, okay? And so let me show you that table. So this is that, oops, sorry. This is the table that I was making reference to. So you can see the different elements. So these are the specific heats of all of these different elements. If we look at water, because it's phase dependent, so we have to pay attention to the phase that we're in to determine which of the C's that we're going to be using, okay? Okay, so and if we look at the units for C, the units are going to be joules, grams, degrees Celsius. Okay. Sometimes, again, you'll end up having joules, moles, degrees Celsius. Or you'll have joules, grams, degrees Kelvin. Okay. Now, since we're making the change in temperature, that delta T, so it won't matter whether it's in Celsius or in Kelvin, because that change in temperature is going to be the same. whether it's Celsius and Kelvin. Okay. But if it's in Fahrenheit and they give you the units in Celsius, you're going to have to pay attention to that. You have to make that conversion first. Okay. So you ready to test this out?
Yes.
Okay. How much energy is required to change the temperature of 25.0 grams of water from 10 degrees Celsius and 50 degrees Celsius? Okay. So we're looking at how you're going to change the temperature of water from 10 degrees Celsius to 50 degrees Celsius. Okay. So what do you think we're going to do? So we know that we're going to be using this equation, right? We know what the definition of delta T is, right? Because we talked about that 2 weeks ago. So we know delta T is going to be equal to T final minus T initial. So what is our T final?
The 50 degrees.
Okay.
And then it'd be minus the 10.
Okay. So we know our mass, right? Mass is given to us, so we know what M is. And we're going to go to C, find that C on that table. So let's go back to that table. Oops, wrong way. Okay, so we're talking about liquid. Oops. Okay, so we know it's from 10 degrees Celsius and 50 degrees Celsius, right? And we said that water boils at what temperature?
100 degrees.
Okay, 100 degrees. And we know, so if it's below 100 degrees, but above, what temperature does water freeze?
Was
Zero.
this true?
Okay, that's right, 0 degrees, actually, 0 degrees. That's right. And so since water freezes at 0 degrees, so we know that since we're in 10 to 50, that's going to be the liquid phase. So then we're going to use this 4.18 for our Q. So we're going to put our Q here. I mean, our C, sorry, our C. That's going to be of water. So we'll put a W for water or liquid. So that's going to be equal to 4.18. Do you guys remember the joules? I mean the units.
The joules over gram times degrees Celsius.
Yep. Joules, grams, degrees Celsius. Okay. So now we have everything that we need to do the calculation. Okay. So we'll just plug it in this equation down here. Let's bring it up. Flip it over. Okay, so we have our mass, which is going to be 25.0 degrees. I mean, 25.0 grams. Yeah, long day. Multiply by our C, which is 4.18 joules, grams, degrees Celsius. And then we have our delta T, which is going to be 40 degrees Celsius. Okay, so our degrees Celsius are going to cancel out. Our grams are going to cancel out. And then we're going to be left with just joules. Do that calculation. So what do you guys end up with?
I got 4,180.
Okay. And that would be joules. Okay, questions?
So you
Can
said
put-
we would just
Oh,
like
go ahead.
leave it as a like the whole number. We wouldn't like simplify it down.
You're saying like make it into kilojoules or to, so you could make it into kilojoules to make it a smaller number. So a 4.18 times 10 to the third, that would be fine, or you can leave it as it is. And in this case, since there's three significant figures, you already had three significant figures.
Oh, okay.
Make sense?
Yes.
Good, good, good. And so, like, when we talk about heat, this is one of the easier concepts to kind of grasp because it's just it's two simple equations, right? So we've talked about when it's transitioning, right? Going from one phase to the other. And when we talk about when you're within that phase, you're staying within that phase. Okay. So it does get a little more not rigorous when you're going through from a very low temperature and you're changing phases because you have to take other things into consideration. You have to take the fact that you're changing phases into account as well. Okay. And we're going to talk about that here in a second.
Sorry, I had a question.
Mhm.
So for you said this one would be in like it could be asked for like in moles as well. So instead of the 4.18 joules over the 1 gram, we'd use like the atomic mass.
Yeah, so you would, in this case, it would actually be, yes. Okay, so if it was given to you in moles, then let's say your value was in moles, that value for C was in moles, then you need to change your mass into moles by dividing by the atomic mass. That's right.
Oh,
Just like we did earlier.
okay, thank you.
So it's gonna be similar concepts. The only thing that your C value is going to be different than what you have for your delta heat of vaporization, right? And then your C value is going to be different than when it's in grams. But you should end up with the same amount of energy if it was done correctly. Okay, so let me clear this so you can actually see the text. Okay, so as I was saying, that when we start taking into consideration change in temperature in addition to change in state, so then we're going to have to take all of those into consideration. So if we're starting off with ice and we're going to steam, we have to take the fact that we're going to be changing from ice to liquid, and then also that we're changing from liquid to gas. So those heat vaporization and the heat of fusion are going to be important for that. Let me show you what I mean. So if we had a case where we had, let me write the question out for you. Okay, so 25.0 degrees, 25.0 grams of ice is heated to 120 degrees Celsius, starting at minus 10 degrees Celsius. How much energy will be needed? Okay, so this is the problem that we're going to be working here. And we're going to try to take up as much space as we can to get that done. If I move this above, can you guys still see it? Like if I move it a little bit higher? Like right there? Can you guys still see the question?
Yes.
Okay, good. Okay, so we're going to be going from a solid state because it's negative 10 degrees Celsius. So since we're going to be starting from a solid, we're starting somewhere down here. So we're going to assume this is about 10 degrees Celsius. Okay. And we're going to be going to first 0 because that's where we get our transition state. We're going to change from a solid to a liquid. Okay. So minus 10. And then this is going to be at 0. Okay. And then we know that water boils at what temperature again?
100.
So this is the point where water is going to be boiling. Is that 100? And we're going all the way up to 120. So I'm going to assume this is about. Okay. So we're going to have to break it up into stages because we have 2 places where we're making transitions. Okay. So we start with our minus 10 and to 0. So that's all in the solid phase. So we're going to be using the Q equals MCAT equation. Okay. So, and in this case, we're going to be using the C for ice. Okay. And so if I remember, the C for ice is going to be, I'm going to put these on the side over here. Let me know if you can see them or if you can't. It's going to be joules, grams, Celsius. I don't have a degree, so yeah, got to bear with me there. And then our C water is going to be equal to 4.18 joules grams C. And then our C gas or vapor is going to be equal to 2.00 joules grams C. Okay. Okay. So since that's the case, what we're going to do is we're going to actually plug that in for this one, for the ice. Okay. So we know that we're going from our initial temperature is going to be the negative 10. And then our final temperature is going to be 0. So T final minus T initial. So for this first one, so for our delta T, so our initial temperature is going to be, our final temperature is going to be 0 minus, and then minus, in this case, minus 10, right? So then that's going to be 10 degrees. Okay. We know our mass is 125. So we can go ahead and plug that into this equation. So we can go Q is going to be, or we're going to say Q, and we'll call this Q1 since that's the first phase that we're going to go to. Q1 is going to be equal to 25 0.0 times, and that's grams, times our sea ice, which is going to be type this, times 2.06, and that's going to be joules per grams Celsius, times our change in temperature, which we calculated to be 10 degrees Celsius. Okay. So then if we do that math, what are you guys getting?
I got 515.
Okay. And so we know that's going to be 515 joules. Okay. Now the next one, we know that this represents that change. That we're going from a solid to a liquid. So it's going to be that transition. So in that case, we're going to be using Q is going to be equal to mass times our delta H fuse. So then we know that from earlier, Q equals 25.0 grams times our delta H fuse, which was 333, and that's joules per mole. Joules per gram. So in this case, the grams are going to cancel out. And then we'll get that value. And we're going to call that Q2. And so we know that that was 8,320 joules. So here, since we're going from the liquid phase, so we know the liquid phase is going to consist from 0 to 100 degrees. So we have to take that in consideration here. So then we're going to still use that Q MCAT, but instead of doing it for ice like we did earlier. Now we're going to have to do water because it's that liquid phase. So in that case, we're going to get, excuse me, Q equals 120, 25.0 grams times, so C of water, which is going to be 4.18 grams. And so our delta T in this case is going to be 100 minus 0, which is just going to be 100. A 100 degrees. And then that's going to give us our value for our Q3. Okay, what do you guys get? Can you guys hear me? Or did I lose all of you guys?
I can hear you.
Okay.
I got 10,450.
Okay. So if we have 3 sig figs, that should be 10,400. And
Could you
now,
explain where you got the 100 degrees Celsius from again?
so if we look at our delta T in this phase, since the liquid phase starts at 0 degrees and it ends at 100 degrees. So then our delta T is going to be delta T is going to be T final minus T initial.
Okay, so just be like 100 minus 0, which is still 100.
Yep. Okay, so then we get 100 minus 0, and that's Celsius. So that's just 100. Okay. So then that's our Q3. So then the next one is that transition from a liquid to to a gas phase. So in this case, we're going to be using what equation?
The Q equals M times the H of heat of vaporization.
That's right. So our Q is going to be equal to M delta H, vape. Okay, so let me put that value for the heat of vaporization and we remember that. So that's going to be 2.26 kilojoules per gram. Okay, so then all we need to do is plug it in. So we have 25.0 grams times that 2.26 kilojoules per gram. Grams cancel out. And we're left with, and this is, we're going to call this Q4. So then that's going to be 56.5 kilojoules. Okay, now we'll notice these are joules, these are joules, this is joules, and this is kilojoules. Okay, so at the very, very end, we got to make sure that all of our units match up. But let's go to that last phase first. Let's get that last one. So the last one, we're going from 100 degrees to 120, right? So which equation are we going to be using to calculate the heat there? Going from 100 degrees to 120. Because now we are in the vapor phase.
The Q equals MCAT.
That's right. So we're going to be using our Q equals MCAT. Okay, so we're going to be using this one. And so in this case, we're going to be using the heat capacity of gas or vapor, right? So, and let's see, our delta T is going to be what? How are we going to calculate that?
The 120 minus 100.
Okay, so we're going to have 120 minus 100. So that's going to be 20 degrees Celsius. Okay, so we're going to plug that in down here. We know what our C value is, which is over here, and we know our mass. So we get it was going to be equal to 25.0 grams times 2.00 joules per gram time our delta T, which was 20 degrees Celsius. Okay. And so the units are going to cancel out. We got my Celsius down here. Okay. Okay, what did you guys get?
1,000.
Okay. So we know that's going to be 1,000. So we're talking about 3 sig figs. So it's probably best if we change this to 1.00 times 10 to the 10 to the third power. Okay. And that's joules. So and that's going to be our Q5. Okay, so at the end, to get the whole amount of energy that we're going to need, we have to take our Q1 plus Q2 plus Q3 plus Q4 plus Q5. And that's going to equal our Q total. So we're going to call it Q tot for total. Okay. Now, the thing is that now we know that these guys are in joules. This one is in kilojoules. So we can change everything to kilojoules, or we can change everything to joules, but those units have to match up. So if we know everything else is in kilojoules, so maybe we should just add them all up and put them in kilojoules. Or it may be easier for us just to, change all of these to kilojoules and then add them all up as kilojoules. Or we could just change this one to joules since all the other rest are in joules. Okay, what do you guys want to do?
Change the 1 to joules.
Okay, so let's go ahead and change this one to joules. So we know that if we have 56.5 kilojoules. So 56.5 kilojoules. We're changing those to joules. We know that for every 1 kilojoule, that means that we're going to be 1,000 joules. So that's going to be 56,000 or 56,500 joules. Okay, so then now everything is in joules, we can just add it all up. So let's go ahead and put this board, and then you guys start doing those calculations. O, our Q total, is going to be equal to Q1, which we got 515 joules, plus Q2, which we got 8,320 joules, plus we have for our Q3, 10,400 joules, plus our Q4, which we have 56,500 joules, plus we got our last one, which was 1,000 joules. Okay, so we add those all together. And we want to make sure we have everything all lining up. So then we can figure out what's going to be our number of sig figs. So we take a look. So significance. Okay, so our significance is going to end after the 100. So because these guys will actually, no, let's see. No, that's technically that'll be a decimal point here. So I'm going to draw a line to let us know the sig figs for this one. Okay, and we know that the sig fig for that one is going to be here. Sig fig for that one. So if we take a look, so the 100 spot is where our significance is going to end for everything. So right in that spot. So when we add it up, what did you guys get? I got
76,735.
That's right. That's exactly what I got. So oops. I'm struggling today. Oops, too far. $76,735 joules. Now with sig figs, with significant figures, that's going to be equal to, because like I said, the significance is going to be ending after the between the tens and the 100 spot. So then it should be 76,700 joules. And that should be your answer if we left it in joules. Okay. Questions? Concerns? Cash? Cocktails? Okay, good. Was it a lot?
Yes.
Yes. Yeah. So these problems, they take a while because there's multiple parts that you have to calculate. But that's the process of doing it. Painful, but it gets you the answer that you need. Okay?
So we would only be doing all of this if it's like the degrees are in different like states.
That's right. So if you're changing your state, then you'd have to do it that way. You may get one where you're going from ice to liquid, so then you only have to stop at liquid. You don't have to worry about the gas, right? So you want to pay attention to that too. Whether you go through all the states or whether you just go through one state to one state.
If you go through ice, from ice to liquid, would you just go up to the Q equals MCAT the second time?
Yep, that's right here. So you'd go here. Then you go up to this point, yes. So you do this one and that one. That's right. Oops. Okay, so when you go through this process, the first thing that I always like to do is to sketch this little graph, right? It helps me understand that there's transitions. There's going to be two transition states that we have to go to. And then you just mark off where your temperatures are at. You notice that that's one of the first things that I did. Where's my boiling point? Where's my freezing point? You know, so you mark those off so you know where they're at. And then you just work your way through the process. You find your if you're within the range, if you're increasing in temperature of that phase, then you know that you're going to be using Q equals MCAT. If you're at a transition state, you're always going to be using mass times delta H, right? So then what I want you guys to do is I'd like you guys to do the same thing for this this one, okay? This calculation that we just did. Same process. I'm going to let you guys work together as a team. You guys can discuss it with each other. And you can actually write on my screen, and that's what I would like you guys to do by hitting the term, it says annotate. If you guys go to there at the very top of the menu, it says you are viewing Dr. Henry's screen, or you're viewing, and it'll be a little green button or a little tab. You click on that, and you'll see either three dots or you'll see options. So if you click on that, you'll see a term annotate, ANNOTAT, and it's going to give you options to draw. So you'll have an arrow, you'll have a plus, you'll have a text, and you'll have a pencil. You want to use that pencil. And then once you use that pencil, you can write on my screen. So what I'd like you guys to do is show me that you guys can write on my screen. So we have 2 of the 5 people that are here. Anybody else can write on the screen? And I think if you're using like an iPad, you can use the pencil in the corner and you should be able to write on the screen. Okay, good. Okay, so now that you guys are able to write on the screen, I want you guys to discuss what you guys need to do to solve this problem. And then I want you guys to work on it. Okay? Okay, go team, go. I'm gonna step out, or I'll still be here, but I'll give you guys a little privacy. And I'll give you guys about 10 minutes to do it. Now, discussion means discussion. You guys can do it by text or you guys can do it by talking, but discussion means discussion.
So I just started with looking at the graph and seeing how far or how many times you have to use the different equations, and that's what I'm writing down to make it easy, I guess. So for the first equation, I got 19.6 times 2.06 joules over grams times degrees Celsius times 12 degrees Celsius, if anyone else got that.
Did you say 2.09 for the joules?
No, it was 2.06. I got it from the graph he showed us earlier.
Okay, you're wrong then. Hold on.
So how's it going? Can you guys hear me?
Yes, I had a question. So for the first answer, I got 484.512, but would I end it at the 484?
So you have, let's see. Yeah, 3 sig figs, that'll be fine. Yeah.
Okay.
Okay, so you guys ready to get started?
Yes.
Okay, so explain to me, what are we gonna do?
Sorry, what was that?
I said, explain to me, what are we going to do?
I looked at the graph to see how many of the formulas I was gonna have to use.
Uh-huh.
Here.
So how many formulas are we gonna have to use?
I think 4.
Okay. Are you sure?
No.
No. Okay. So let's go back to that graph. I know you guys are still working. I see the smoke coming, so that's a good thing. Let's go back. Okay. So if we're going from -12 to 115, ice freezes at what temperature?
Sorry, what was that?
Ice freezes at what temperature?
0?
0, that's right. So ice freezes at 0 degrees Celsius. So we know that -12 is below 0 degrees Celsius, right? So if we're going from -12 to 0, that's going to be our first one. So -12 to 0. Okay. So that's going to be our Q1. And so what are we going to use for our Q1? Which equation?
The Q equals M cat.
That's right. So we're going to use the Q equals MCAT. Okay. And then I'm going to move the work that you guys have done, you guys have started. And then what point does water boil?
100 degrees or 100 degrees.
100 degrees. Okay. So we know that this is going to be our Q1. We also know that this is going to, the middle part, which is the transition, that's going to be a Q2. Q3 is going to go from 0 to 100. Q4 is going to be the transition. And then Q5 is going to be 0 to 115.
So if it goes over 100 degrees, we would use the last equation for the gas.
That's right.
Okay.
Okay. So then we have all of our constants listed up here. And again, they'll be given to you. I forgot to put them on your board earlier. So you guys have to look at your notes. That makes sense. Okay. Okay, so then our Q1, let's go ahead and put that in here for our Q1. Q1 is going to be equal to, and you guys had, let's see, Q1, which is ice, and you guys already have it up there. So it's that 119, I'm sorry, 19.6 times 2.06, and that's joules, grams, degrees Celsius, per gram degree Celsius. And then the change from 0 minus 12 is going to be 12. So then you guys got 484 joules. So exactly what you guys have up here. So that's going to be that first one, right? That one is going to be 484 joules. Okay. Now our second one, I saw somebody had been working on that one. So that's going to be 96 grams times 333 instead of 34. And you guys got, what's the value? So you got to help me out that, Graciela. Is your Q2 is going to be,
I got 646 for that one.
is that 6? You said you got 646?
That's
Or
0.8, but I just left the 0.8 out.
6,546, right?
No, that's not what I got.
Okay, 19.6 times 333, 6,526. So that should be 3 sig figs. So it should be 6,530. You go 3 sig figs. So, right, because it's Graciela, you actually had it right. Only thing that number was, let's put it back up here. So we're talking about this middle phase. So we had Q is going to be equal to M, and I need a space for my delta H, and that's delta H use. Oops. And that's going to be equal to 119.6 grams times 333, and that was joules grams. Okay. And oops, and we end up getting the value that we have at the bottom. Equal to 6530 joules. Okay. So what about Q3? What are we going to do for Q3?
Would it be the 19.6 times the 4.18 joules over grams times the degrees Celsius?
Okay, so we have Q3 is going to be equal to 19.6 grams times, we have, you said, since it's water, right? We're in the liquid phase. That'll be 4.18. Times, and so in this case, we're going from 0 to 100, right? So then my final temperature is going to be 100. 100 minus 0 is
100.
100. Okay, so that's Celsius. This guy is joules grams Celsius. Okay, and so we end up with 19.6 times 8 times 100. This is what I ended up with. 8, oops, sorry, the wrong spot. 8,000. And how many sig figs should we have here?
3.
Okay, well, 8,192. So then that would be 8,190 joules for my Q3. Okay, so then my Q4, which is what's happening at this stage right here. As we go from liquid to gas. So that's called our transition stage. So which equation are we going to use here?
The Q equals M times the delta H FAP.
That's right. Okay, so then we have Q times the mass. So 19.6 grams times our delta H VAP, which is 0.26, and that's kilojoules. Kilojoules per gram. And that's going to equal 4. Okay, and then that's going to be in kilojoules. And then our Q5. So what are we going to use to go from 100 to 115 degrees?
Sorry, what was that?
So for our Q5, what are we going to use to go from 100 to 115 degrees?
The Q equals MCAT?
Okay, we're going to use our Q equals MCAT. Okay, so we know that the mass is 119 point, I mean, not 119, 19.6 grams times. So in this case, the C, we're going to be using which C?
The 2.0, which would be the steam.
Okay. That's joules grams per gram Celsius. And then times our change in temperature. So our final temperature is 115, and we started out at 100. So 115 minus 100 is
15.
15 degrees Celsius. Okay. And so we end up with I get 588 joules. Okay. So what do we need to do next before we add them all together?
Change the kilojoules to joules.
Okay, so we need to change the kilojoules to joules. So we have what, 432. I mean 443, sorry, 43.2 kilojoules. And then we know that for every 1 kilojoule, how many joules would that be?
1,000.
1,000.
I have a question. Sorry. I don't know if I got it wrong. So I put the 19.6 times the 2.26 in the calculator, but I got 44.2.
Got 44? Let me check. It's been a long day. Yep, you're right, 44.2. So then that would be 44.3. Right? Because it's 44.296. So no, you didn't make a mistake. I made a mistake. Three. Okay. So we end up at 44,300. Okay. Okay, so now what's our last step?
We add them all together.
Yep, we get our Q total by adding them all together. Okay, so we have 448. I mean, sorry, 484. It has been a long day. Plus Q2, which is 6,530. plus Q3, which is 8,190 plus Q4, which is 44,300 plus Q5, which is 588. And that's going to equal okay, so I added them all together, 6,092. And that will be joules. And so if we look at our numbers, significant ends, this will be after that 0 right here. Significant ends after this 0 here, after this 0 here, and then these guys all three are significant. So then the one that gives us the worst case scenario would be after, it would be here. So we'd use that number to decide. So we're going to use the number after this one to determine whether we round up or leave it alone. So then that final value is going to equal to 60100 joules. Or if we put in kilojoules, we just divide it by 1,000. 60.1 kilojoules. Okay. Questions?
No.
Again, it's just a long question, right? You're guaranteed to have at least one of those on the exam. One long. It may not cover all of the phases, but it is a long one. Okay. Can I erase, or do you guys need a minute to get that all down? Okay. That means I can erase. Oops. Okay. So we're almost there. We're down to our last few slides. I have 30 minutes to work this last part in, work my magic. Okay, how many of you guys have a partner or a significant other or even a sibling?
Me.
How often has your sibling put their cold feet on your back or on your legs or on their cold hands on your face? Or maybe you've done that to them. Anyone?
I've done that before.
Okay, so we've all done that at some point, or somebody's done that to us, one or the other, right? So I had an ex-girlfriend. She had the coldest feet ever. She'd always put her feet on my back. And and it was freezing, right? So the thing is that when she put her feet on my back, why did she do it? Why do you guys think she did it?
To get warm.
To get warm, yeah. It wasn't completely to be evil, but it was to get warm, right? And so what's happening to my back? Her feet is getting warmer, but what's happening to my back?
You're taking in the cold.
I'm taking in the cold. So what happens is because since I'm warm, I'm typically really hot at night, and she's really cold at night. So then what she'll end up doing, she'll put her feet on me to warm it up. And so what's happening is that we're going to get the heat is going to be transferred from me to her. So her feet gets warmer, and then my back gets colder. Okay. And so as long as she keeps her feet on me, we're going to reach a point of equilibrium. Her feet gets warmer, my back gets colder. They'll meet a central point, a point where they're both the same. Okay. So this is called thermal equilibrium. This process is called heat transfer. There's whole fields of study that is dedicated to heat transfer. Fortunately for you guys, we're not going to go through all of that field. But I want you to understand that in this concept, the heat that I'm losing, she's gaining. Okay. Again, I'll say that the heat that I'm losing, she's gaining. Okay. So, in other words, heat or energy is never really lost, it's being transferred. Okay. So, this brings us to the laws of conservation. We have the laws of conservation of mass and energy, which basically says that overall, if we looked at everything in the world, right, mass and energy is going to always be conserved, right? That means that it's going to be fixed and it doesn't change. If we look at just the law of conservation of mass, law of conservation of mass basically says that the total mass in a reaction, in a chemical reaction or a chemical change, is going to be equal to the total mass that's being produced or the products. Okay. So, in other words, what you're going to be putting in, you're going to have to get out that same amount once you have your products. Okay. And that kind of helps us with that balancing of chemical equations. What you put in, you have to get out. So, and then the law of conservation of energy essentially says the same thing. What you put in, you have to get out. But a lot of times we'll just say it as the energy in a system is going to be conserved. So it's neither created or destroyed. It's just going to be changed. Okay. You guys good on that?
Yes.
So when we're writing thermochemical equations, we have to take in consideration that energy, or we call it heat, like I said earlier. So we've already been introduced to enthalpy. So this is called the heat of the reaction. It's typically delta HR or delta HRN or delta HRXN. So you'll see them written a couple of different ways. Okay. And again, we know that that's going to be enthalpy. And this is going to represent the enthalpy or the heat of our reaction. Okay. So it's going to be part of our reaction. So if the heat is being released, it's going to be exothermic and it's going to have a negative value. Okay. If the heat is being added, it's going to be endothermic and it's going to have a positive value. So here's an example. So this chemical is called ethanol. I mean, not ethanol, ethane. So this chemical is called ethane. Ethane, two ethanes reacting with 7 oxygens produce 4 carbon dioxides and 6 waters. So this reaction, since it's a negative value, it's going to be exothermic. So energy is going to be released. And this is 2 ways of writing this equation. So one, we could write a thermochemical equation by putting the enthalpy on the side, or we can put it within the equation. So in this case, we have 2 ethanes reacting with 7 oxygens. It's going to yield 4 carbon dioxides and 6 waters, and it's going to release 2,855 kilojoules of heat. Okay. And so again, this is an exothermic reaction. So in the case of an endothermic reaction, this is the case of ammonia. So when ammonia is broken down, you need to add 92 kilojoules of heat to produce nitrogen, 1 nitrogen, and 3 hydrogens. Or we could sit there and say it, have it on the side where we have 2 ammonia yields 2 nitrogen and 3 hydrogens, and the enthalpy is going to be plus 92 kilojoules. So even though that they have it written as just kilojoules, it really should be kilojoules per mole. And so it's going to be based upon 1 mole of substance. And so that's the same thing over here. Or we can say kilojoules per gram, you know, depending on the correct units. But in this case, this will be kilojoules per mole, since it's in a chemical equation. Okay, questions? Okay, great. Okay, so here's a question for you guys. The thermal decomposition of limestone, so solid calcium carbonate, and it's CaCO3, and S represents the solid, to lime, which is solid CaO solid, and gaseous carbon dioxide, is an endothermic reaction requiring 178 kilojoules per moles of calcium carbonate decompose. Write the thermochemical equation in 2 forms. Okay, so what are my products in this case? Now we're at the last part of the class. You guys can't tap out now. We got 3 slides left.
Would it be like, would one of them be the solid calcium carbonate?
Okay, so we have the solid calcium carbonate. So would that be a reactant or would that be a product? Because read what it says. It says the thermal decomposition of limestone, which is this compound, solid calcium carbonate, to lime, which is solid calcium oxide, and carbon dioxide.
So would it be a reactant?
So that would be a reactant. So this part is going to be our reactant. So that's going to be CaCO3. And then we have solid. And then that's going to, since we know that that's our reactant, and this says to, that basically means that you're making this, right? Or you're decomposing it to this. So that means it's going to be products now. So we have CaO solid plus carbon dioxide, CO2. Okay? You guys see that? Is that balanced?
Yes, I see.
Is it balanced?
Yes.
Yes, it is. We have 3 oxygens on our product side. We have 3 oxygens on our reactant side. We have 1 carbon on our reactant side and 1 carbon on our product side. We have 1 calcium on our reactant side, 1 calcium on our reactant side, and then 1 calcium on our product side. Now, if we're going to write the thermal component, we can write it within the equation. So they tell us what type of reaction it is. It's an endothermic reaction. So does that mean it's on the product side or the reactant?
Would it be on the reactant side?
It's going to be on the reactant side because it's positive, right? Since it's positive, we're going to be putting it in the reaction. So we'd put it over here, 178 kilojoules per mole.
I have a question. So when you ask balance, is there ever a time where they like we would get a problem like this where it's not balanced?
Yes. And so typically they're going to give you the chemical compounds, so you don't have to worry about figuring those out. You guys are not at that level yet. You will be, but you're not there yet. And then they'll do something like this, where you have to write the chemical equation and you have to make sure it's balanced. Okay. And then what is the other way of writing the reaction? Come on, we're on our last 3 slides. Almost home.
I forgot what it was, but wasn't it just the empathy of something equals 178 kilojoules?
Right. So our delta H of the reaction. So even though it's written like this in your book or in this part, it really should be on the outside. It should be here. And you'll see it actually, in all honesty, it can be written both ways where the R is there or the R is here. And I always put RX in for reaction. You can use RXN, you can use R, you can use RN. They all mean exactly the same thing. It just depends on the book or the book that you're learning. And so our delta H, is it going to be a positive or negative value? Is that 178 going to be positive or negative?
Positive
It's going to be positive. And why is it going to be positive?
because it's endothermic.
That's right.
So if it's exothermic, it would go on the product side.
No, you'd put it here too. You can put it on the side here too, but you'd put a negative value. Right? And then, but over here, the first reaction, if it was exothermic, it would go on the product side.
Okay, yeah, that's what I said. Okay, thank you.
Okay. Questions?
No.
Okay, good. Okay. Here it is. These are going to be the last 2 slides. We're almost there. Okay, so what is the mass of liquid octane? So octane is C8H18. A component of gasoline must be burnt to provide 9.05 times 10 to the 4th kilojoules of heat. So the heat of reaction is going to be equal to negative 5,471 kilojoules per mole of liquid octane burn. Okay, so if we're writing we don't have to write the full equation, so that's for what. Okay, so they're giving us the heat here. They're telling us our enthalpy is this value, right? And this is how much energy that we're going to get, right? And so which equation do you guys think we're going to be using? Q equation do you think we're going to be using? You have two possibilities, either Q equals MCAT or Q equals M or N delta H.
I think it's the Q equals M times delta H.
Okay, so it's going to be the Q equals M delta H. Okay, but in this case, instead of using mass, we're going to be using moles. Okay, and then we'll work to mass. Okay, so we have M delta H, and then in this case of our reaction, RxN. Okay, so we're provided this, and we're provided the Q. This here represents our Q, that's our heat, since we know that the units of heat is always going to be joules, so that's going to be Q. And then we know that this is our delta H, and we want to solve for our M. So we have M equal Q divided by delta H. Okay, so our Q value is 9.05 times 10 to the 4th joules, sorry, kilojoules, over 5,471 kilojoules per mole. So this is going to give us moles because the kilojoules are going to cancel out, the moles are going to flip up. And we end up with 9.05 horsepower. $5,471. So we're going to end up with 16 point, and there should be 3 sig figs, 5 moles. Okay. Now we know that moles is not mass. Moles are quantity. So what do you guys think we need to do to get the mass? Get it earlier.
I have a question before that. Would the 5,471 still be negative or no?
So the negative just tells us what side of the reaction it's going to go on. The quantity is going to be that quantity, right? It lets us know whether it's endothermic or exothermic. But when you're trying to calculate mass, you can't have a negative mass. Does that make sense? So you're
Yeah.
going to use the absolute value.
Okay.
Good question. Okay, so we know that this is a methane, right? Which is C8H18, not methane. Yeah, methane, not methane, octane. And it has been a long night. We're almost done. I apologize for not being at my top performance. Okay, so what do you think we're going to use to get to mass? Let me give you a hint. You may have a periodic table. So what on the periodic table are we going to use to get to the mass?
Is it the atomic mass like what we did earlier?
That's exactly right. We're going to use the atomic mass. So how many carbons do we have now?
8.
We have 8 carbons. How many hydrogens?
18.
We have 18 hydrogens. Okay, if we go to our periodic table, oops, I don't want it. We go to our periodic table, we have carbon. Carbon weighs 12.011. So let's go ahead and write that down. There. And we're going to be multiplying that by 8. And then hydrogen weighs 1.008. And we're going to be multiplying that by 18. Okay, let's go back to that problem. Okay, so 12 times 8.001. So that's 96.088. And then 1.008 times 18. That's going to be 18.144. And then we're going to add both of those together. We get 114.232. The units are grams per mole. Okay, so we want to get to grams, so grams are going to go on top this time. So we have 114.232 grams over, since that's per mole, so that'll be 1 mole. So moles are going to cancel out. And we're going to be left with just grams. So 60.5 times 114.232. So we end up with 1,800. And since there's 3 sig figs, it should be 8. We have a 4 following it. 0.828. And that would be grams. So we're going to use this number here to decide whether we round up or leave it alone. So in this case, it will be 1,880. And that would be grams. Okay, questions?
No.
Concerns? Okay. So I'm going to go ahead and clear. And then we are done. Except for our summary. Okay, so we've talked about the law of conservation, right? So in the law of conservation, we know that it's about matter and energy. Both of them are going to be conserved. So basically, what you're going to be putting in, you have to get out. So we also know that in the case of energy, energy can be transferred from different forms, but at the end, it always has to add up to the same, okay, of that system. So here's an example. So you guys are powering everything in your house, right? So what happens is that we use natural gas to start that boiler, right? The boiler then makes steam. That steam then turns that turbine. A turbine charges that generator. That generator provides electricity that you guys can use for your lights, your range, and your TV. So the energy that we're producing here is just being transferred. Okay. So this concept of conservation of energy and matter, that's what chemistry is about. So welcome to chemistry, guys.